Hello, everyone. My name is Gilroy, and I'm joined with my colleague Phil Taylor. And we're going to deliver a webinar on CMOS sensor specifications and how they play out in scientific imaging applications. What is the goal of this talk? It's primarily to define most of the key high-speed CMOS sensor specifications that you need for your scientific imaging application. We also want to exemplify how these specifications affect these imaging applications. So to do that, the topics we're going to cover include defining what is temporal resolution, spatial and light level, understanding the spectral responsivity curve, which is essentially a combination of your pixel area, quantum efficiency, and your fill factor, discussing the sources of noise in high-speed CMOS sensors, primarily the two dominant sources, a look at both signal-to-noise ratio and dynamic range, and then we'll finish by talking about some support and knowledge bases we have, including key documentation, applications notes written by our team, and also training courses and more. There has been a rapid technological development since 2009. If you look at the throughput of an image sensor, and throughput is simply at what resolution you're recording at and frame rate. So for example, a 1 megapixel camera, if it runs at 1,000 frames per second or a kilohertz, it'll have a 1 gigapixel a second throughput. In 2009, we were able to achieve 7 gigapixels a second. 2011, we got to 12 gigapixels a second. 2014, we came out with the V2512, which was your 25 gigapixels a second. And finally, we arrive at our flagship camera that we have today. 2021, we have our TMX, which does 75 gigapixels a second, which, to give you an idea, again, that's 75,000 frames a second at 1 megapixel resolution. In order to achieve that type of throughput, the primary design challenges that needed to be overcome were just being able to get that data off the sensor, so to elevate that throughput. When you go this fast, you also need to improve the light capturability, right? So the faster you go, the less light you have. We needed to go from a front side illuminated technology to a backside illuminated technology. And at the same time, we need to maintain image quality at that speed. And then just as important as your image quality is your timing accuracy. So we want to make sure that we have excellent timing fidelity and timing precision when in standalone cameras and in systems of cameras. Now, one of the most fundamental specifications of a high-speed camera is the frame rate.
Now, while a digital camera typically may have a resolution of, say, 12, 21, or 36 megapixels, high-speed cameras give the option of choosing the resolution that we want. The key benefit here is that as we reduce our resolution, we reduce the amount of data per frame that we have to pull off the sensor. So by that, we are therefore able to increase the rate at which we record individual frames. So as you can see here, our resolution is reduced, and as we reduce our resolution, we achieve greater and greater frequencies of acquisition, or frame rates. And we typically define these in kilohertz or frames per second. So kilohertz because we're dealing with thousands of frames per second, or frames per second as FPS. Then some sensor architecture also allows us to activate a mode called binning. And binning allows us to achieve higher frame rates as a different image ratio by combining some pixels together. So how then do we choose our frame rate? When we choose a frame rate for quantitative analysis, we want to then temporally resolve any critically contributing moments that may occur within a larger event. In this case, we would choose a frequency which allows about 3 frames for that moment. And we may well discover temporally shorter events that we were previously unaware of. in which case we would then reset our frame rate requirements. If we want to do some computation measurement of the flexing of this tablet when it impacts, for example, the image on the left at 320 frames per second leaves us missing critical moments in time when we assume some important data could have been recorded. On the right, we are now imaging at 3,200 frames per second, and we can have a level of confidence there that this frame rate is suitable for our application requirements.
Exposure time is the total time per frame that pixels are open to collect light. Now, if you look at this in terms of raw signal, this is just a typical example of our 75 gigapixel throughput camera. At max exposure and at max resolution, we will be at 13 microseconds. So every time a frame is captured, the max exposure will be 13 microseconds. All right. If we go all the way down to the minimum exposure time that we can achieve for that system, we can arrive at 38 nanoseconds. All right. And what you'll see is on this graph, as you decrease your exposure time, you will decrease the raw signal on your sensor. All right. So some of the key takeaways from this is you want to remember that the exposure time regulates how many photons are collected per frame. The max exposure at a given frame rate is slightly less than 1 over a frame rate. Okay. The precise exposure value needed is always application dependent. And very often it's deterministic. So if you have a shot looking at a bullet flying across the screen and you want to set your exposure time, you can actually take out a pencil and paper and calculate what your exposure time should be set at. All right. The exposure time is the direct impact on the degree of motion blurring. So an object has the ability to move during the exposure time. So the shorter the exposure time, the less motion blurring you have, but the less light you'll be able to collect per frame. So it's kind of an elegant balance between getting a good brightness and minimizing your motion blur. Now, we like to conceptualize different aspects of the cameras using schematics. So this is a very helpful schematic to understand your exposure time and your frame rate. So this is a signal in the camera called your strobe signal. And the strobe signal is a 5-volt TTL signal that oscillates as a square wave in time. So if you look at every time this square wave goes down, that's the start of an exposure time. It'll stay low and capture photons until it goes back up. That will be your end of exposure time. That green line, which is where your strobe signal is going up, also represents the position of where we place our timestamp information. All right. The rate at which these falling edges occur is going to be your frame rate. Now, for every frame you have in your video, we will have a timestamp associated with that frame. So the format of that is typically hour, minute, second, millisecond, microsecond, and nanosecond. We also give a date and a year. We provide the interval, which is the time in between these edges. The exposure time is also noted. We also give the elapsed time from trigger. So the moment the camera receives a trigger, we measure against that for each frame. So how long did it take for that frame to occur after that trigger had happened? Okay. We also provide each image number. All right. Frame 0 is the frame that comes directly after the trigger. All right. It's also important to remember that exposure time is sometimes referred to as integration time, and sometimes people refer to this as your gate time. So what does motion blur look like, and what is it defined as? It's defined as a directional blurring induced when substantial motion occurs during an exposure. So if that's our reference image, so let's pretend it's static, not moving, and we take a picture of that. Then all of a sudden we record some video, and you see some of the frames have something that has extreme amount of blur in there, right? This is a motion blurred image. Generally, this is unacceptable, and we'd have to rethink the exposure settings to get this right. So the fundamental mathematics behind that is the motion blur, how much it blurs, is proportional to the velocity of the subject, the scale of the image, and the exposure time. If the velocity is very high, or your scale is very high, or your exposure time is very long, all of those things will contribute to having substantial motion blur. Now, what should you really consider when you're setting up your test? Most high-speed tests, generally we want simply 1 pixel blur or less. That's ideal, right? Because you just won't observe it. However, in some techniques like digital image correlation or particle image velocimetry, we generally aim for 0.1 to 0.3 pixels of motion blur that's acceptable. Why do we want that level of motion blur? It's because we use what are called subpixel algorithms to do measurements, and they're going to be sensitive to this level of pixel blurring. In other techniques like Schlieren imaging, pixel blurring may be beneficial. It may help you define the thickness of your shockwave and really define your shot how you want it to appear in your recorded video. But in the end, the set exposure time is always application dependent, and there's no one size fits all exposure for a camera. And just a last note, this is not to be confused with blurring due to out of focus lensing or faulty back focusing. If you see a lot of directionality in your video in terms of your blurring, generally that's going to be a motion artifact. However, if you have very isotropic type blurring or things you can't correct with the motion blur, then it's likely that you need to take a look at your lensing, or maybe the focus rings on your camera need to be adjusted. These are some helpful equations of motion. I'm not going to go through them in detail, but it's very helpful to know if you look at the right-hand side, if you have frame 1 and then frame 2, you can see that you have a deblur, which is the distance that your subject blurs in time. This is during a frame. You also have deframe, which is the distance that the object moves between subsequent frames. All right, so on the left-hand side, you can simply solve for that by looking at the velocity of your subject relative to your frame rate. All right, that'll define the distance that the subject moves between frames. If you want to know the distance the object moves during frame capture, that's going to be simply the velocity of your subject times your exposure time. All right. If you want to know how many pixels it blurs, you're going to need to reference this number against the image scale that you have in your shot, which is going to be related to your set resolution of your camera.
So we've spoken about temporal data and the need to manage both our frame rate and exposure time duration. And in that discussion, we've mentioned a few times resolution and pixels. So let's take a better look at what we mean by resolution and why pixel size may be important to our application. So there are various references to resolution in the imaging world, and it is important in discussions to know what you are referring to. Outside of optical components and their contributions, there are two that we really should consider: the sensor itself and then the resultant image. So the resolution of the sensor is very easy to determine. It is the number of pixels in the X direction multiplied by the number of pixels in the Y direction. And we can, of course, use a smaller resolution in high-speed cameras. We would refer to this resolution as the active sensor area. And to determine the active sensor area, we look for the pixel size in our specification data sheet, and we multiply that by the multiple of pixels in the X and Y direction. And this is important actually for choosing the optics in your application. Now, the image resolution is sometimes referred to as the print resolution, and it is the dimension of the subject plane you are able to resolve and the pixels. So because it is based on the subject plane, we have to take scale into account. So we determine the image resolution by dividing our field of view, the area that we have framed in the shot, by the number of pixels that we have available. Now, by having more pixels across our field of view, we're able to achieve a higher spatial resolution. Higher spatial resolution allows us to define smaller details. It also allows us to output higher accuracy data when we are using algorithms to do processing such as pattern matching. So today, true high-speed cameras typically have a maximum resolution of 1 and up to 9 megapixels. As we pull more data from our sensors, the frequency at which we can pull that data reduces. So there is often a trade-off between choosing higher spatial resolution and higher temporal resolution. So how then do I choose spatial resolution? Well, again, it is somewhat subjective, although there are some restricting factors. We typically need 3 points or 3 gray values in space to determine a feature. We generally view this as 3 pixels, although there are algorithms for some applications that can approximate the position to as high as 0.1 pixel. For detection requirements, we use between 3 to 5 pixels for particles or speckles, and much more if dimensions or shape are required. So here is a very good example of the need for spatial resolution. So in this case, the client wanted to view the entire sidewall of this Humvee tyre, but they also wanted to do some post-processing on the deformation of the tyre. So in this case, the speckle was applied to the tyre, and that speckle needed to be resolved at about 3 to 5 pixels in size for each of those dots on the tyre. And here's another example on a much greater field of view, and you can see on the aircraft here they needed enough detail on the sides of the aircraft in order to do that deformation analysis. And of course, in this case, we also needed to specify the size of the speckle based on the pixel size.
The spectral response curve, by definition, details how responsive a pixel is to incident light across the visible and near infrared region. Every sensor that exists generally has this data associated with it. If you look at this graph, on the y-axis, you have responsivity, which is in amps per watt. And on the x-axis, you have wavelength. All right. Amps per watt is simply your signal current against your incident light power. So you can equate amps to electrons per second, and you can equate watts to how many photons per second are hitting your sensor. So this is a very simplistic diagram to represent what it is we're looking at. Responsivity, by definition, is simply going to be your pixel area times your quantum efficiency times your fill factor. Not that long ago, we used to simply say, how big is the pixel? And that would give you a really good idea for how sensitive that sensor is relative to other sensors. Now, since we have the BSI sensor technology or backside illuminate technology, you can see that even though it has a much smaller pixel, 18.5. It has a much higher responsivity relative to our old flagship, the V2512 front side illuminated pixel. All right, so this is extremely helpful when deciding what sensor you want to have a really high responsivity. There are many sources of noise in high-speed CMOS sensors. The two most dominant sources are called temporal dark noise and photon shot noise. Temporal dark noise is also known as read noise, and it is a signal intensity independent noise source and is actually generated from the CMOS sensor hardware. If you look around at many sensors, you'll see that this number is between 7 and 50 electrons for high-speed CMOS sensors. And it really dominates in terms of specification for applications that deal with low light. Okay. And it also will bundle in to another specification called AST, or absolute sensitivity threshold. So here's an example. This is done in the United Kingdom. This is an application where we have a high-speed camera looking in a flow of blood cells going through a microchannel. So if we simply increase the read noise on this sensor in this low light application, what you can notice is that as we increase the noise, you'll start to see that the relevant information, for example, the blood cells moving through the channel, become obfuscated from that noise source. And if you have a sensor that has too much read noise, it's very possible you cannot see your sample at all. So it's very important to know what the read noise on your sensor is. And also it's very helpful to know what the AST is on your sensor, which we'll discuss later. Photon shot noise is a signal dependent noise source, and it's actually intrinsic to the nature of light. So there's nothing in hardware that we can actually do about this in our CMOS sensors. The photon shot noise actually increases as the square root of this incident signal. This is also called a Poisson behavior. So to give you an idea, if you, for example, look at a Xyla chart, which is a chart that increases in signal intensity as you go from the right-hand side to the left-hand side, and you look at the noise behavior, you'll see that as you increase the signal on the sensor, it will actually increase at a rate of the square root of the signal itself. And if you wanted to know what the signal to noise ratio is, it's simply the signal n divided by the square root of n. And if you simplify that, you'll get the square root of n. So the signal to noise ratio will be the square root of n. Why is this important? It's important because when you look at, for example, your signal to noise graph here, you'll notice that on the left-hand side, it will be dominated by your temporal dark noise. And on the right-hand side, it will be dominated by your photon shot noise. So the signal to noise ratio curves just simply gives you the SNR at each respective signal level across the sensor's range. It also defines, in a sense, how sensitive all the various light levels are to changes in signal intensity. So if you have a very fine detail in your shot that exist in between gray levels, it is this term, this specification, that'll help you to determine if you're actually going to see it or not. The absolute sensitivity threshold, which is shown by the blue arrow on the left, tells you exactly where a signal to noise ratio of 1 is located. It also defines how many photons are needed for you to start seeing an image. And it is actually the best proxy or the best specification for determining the performance of a sensor in low light applications. If you have one sensor that, for example, takes 100 photons for you to be able to see something versus another sensor that requires 1 photon to see something, you're going to want to go with that lower AST number because you're going to be able to get a better SNR performance for that lower AST number. On the right-hand side, with the purple arrow, you'll see the saturation capacity. This is the total number of photons needed to reach pixel saturation. This is synonymous with full well capacity. So this tells you exactly how many photons or electrons are needed to exist in that pixel or to have hit the pixel to give you a full signal right before saturation. This particular graph is from the EMVA 1288 report for the VO 1310, and it's for light at 532 nanometers, green light, with an exposure time of 50 microseconds. The boundary of the AST and the saturation capacity will actually define what is your dynamic range. The bigger your saturation capacity and the smaller your AST will contribute to a wider dynamic range.
So here we have an example for AST, the absolute sensitivity threshold, and we have a fluorescence sample. That fluorescence sample emits 100 photons. Now, if we have an AST, absolute sensitivity threshold of 2, then we can see all of our signal is well above the noise level. Whereas if we have an AST of 100, okay, 100 photons, then we really have the same level of signal as the read noise photons themselves. So in that case, it's very difficult to determine what is signal and what is just simply noise. So here we have another example, PIV, where we have very low light particles on the top left, and then we have some brighter particles on the bottom right. But in this case, we want to do some analysis on the vectors, and we really need to be able to define those values in the shadow values on the top left. Otherwise, we're unable to do this sort of computational analysis of the image.
It's very important to have extremely good SNR, especially at low exposure times. Ballistics is a really good example of that. Ballistics experiments demand that you run very, very high frame rates, thus very short exposure times for impact tests. So here we have a camera set to 1.4 microseconds. And as you can see, it still maintains an excellent SNR performance to see things like the speed at which the bullet comes in, the bullet disintegrates at, and also you can get good information over the size and the size distribution of those frags coming off of that impact. This will give you excellent accuracy for any sort of measurement you're looking to do in your test.
So we mentioned dynamic range, and the dynamic range is the minimum detectable signal through to our maximum detectable signal. So it is the ratio of the largest measurable signal intensities to the smallest. Okay, so here if we have 100 photons as our SNR of 1, so that's our minimum, that's our AST, and then we have the maximum signal before we tip over to saturation. That is our SNR max. And here the example is 100 photons at our AST and 20,000 photons at our maximum signal. Therefore, the dynamic range is 20,000 to 100. So that correlates directly to our full well capacity over our read noise.
One thing we see often confused in the field is the difference between dynamic range of a sensor versus the bit depth of an ADC or an analog to digital converter. Dynamic range of a sensor is different than the bit depth of an ADC. The bit depth of an ADC is actually selected to oversample the dynamic range of a sensor. It generally comes in 8, 10, or 12-bit values, and it corresponds to 256, 1024, and 4096 possible levels, respectively, that you can get on your sensor. While the ADC can produce this number of light levels per pixel, the sensor in actuality cannot produce this level of grayscale detail. This is going to be limited by the dynamic range of your sensor, as defined below. It's going to be your full well capacity, which is the total number of electrons that you can fit on a pixel before it saturates, divided by the minimum noise level on your sensor, which is your read noise. This is going to define how many light levels you can actually see and resolve during your test. All right, so to give you an idea, this is why we actually specify the two values independently. The VO1310, for example, has a 12-bit ADC while having a 9.7-bit dynamic range. So if light level resolution is critical in your experiment, do not use the bit depth of the sensor. You're going to want to inquire about the dynamic range of that sensor. On the right-hand side, you'll see a series of photographs. I'll show you. This is produced by a 10-bit ADC camera with an 8.5-bit dynamic range. If we keep the ADC the same, but decrease the bit depth of the dynamic range down to 7, you'll start to see you're going to lose some gray level information. And if we decrease it all the way down to 6.5 bits, you'll notice you'll get a very old TV-like look to your shot, okay? So again, the key takeaway is dynamic range is different than your bit depth of your ADC. This is an example where imaging explosives could really push the limits of your sensor's dynamic range. On the left-hand side, you see before the shot, you can see no item visible in the frame. As you go from the left to the right, the explosive device emits a lot of light upon ignition and eventually leads to oversaturation. This is a perfect example where the dynamic range of the sensor is simply not enough to characterize this event. The details of the object are lost to the shadows, and the details of the brights are lost to oversaturation. All right, so another way of saying that is the evolving scene brightness range goes beyond the dynamic range of the sensor. This could be remedied by adjusting the scene or by the sensor parameters. You could investigate using lighting, filtering, multiple cameras, techniques such as EDR, HDR, and others. And this is generally exacerbated with cameras that have very low dynamic ranges or those that have very high ISOsat values. ISOsat values simply tell you how fast your sensor saturates. Here's an example done in collaboration at NASA Marshall, where we looked at a rocket motor firing. Now, as the operator, I had to choose whether I wanted to expose the rocket motor for good quality, or if I wanted to get good detail of the flame. Now, since we were interested in the plume, I adjusted the exposure time of the camera to 1 microsecond to get good information about the flame. When I did that, you can see that the rocket motor itself got lost to the shadows. Schematically represented to the right, you can see that we have the dynamic range, where the brights sit nicely in the upper part of that range, but the background is far below that of the dynamic range, which you cannot see. One really neat technique you can do called HDR, right? And this is a application note that you can look into with Vision Research. This is the HDR technique. So what we simply did was we took 2 cameras, synchronized them at frame rate, had one camera set to 1 microsecond, the other set to 120 microseconds, and we simply used a Python script to combine the frames in post to result in a video that had a much higher dynamic range, hence the HDR technique. This can be easily done using any stereo pair of cameras that are synchronized. Sensors also have non-uniformities across the surface. This is generally summed up as PRNU and DSNU. Photo response non-uniformity and dark signal non-uniformity. While we do intend to design every pixel exactly the same, this is never the reality. All right, so these two terms characterize how non-uniform pixels are at the low light level or no light level and in the mid light level. So generally 50% of the full well. Okay, so the DSNU 1288 gives you the spatial standard deviation of the dark signal, generally in units of electrons or digital number. The photo response non-uniformity, or PRNU, gives you the spatial standard deviation of the photo response non-uniformity in percentage from the mean. So to give you an idea, if you look at the images on the right, this is an image that was remapped from gray to let you see the non-uniformity of the sensor. On the bottom right, you can see a graphic that just shows you, although you have 5 pixels that are exactly the same on the sensor in terms of size, specification, in reality, the responsivities could be a little different. All right. So in other words, their slopes versus signal will be different. If you look at that blue line, while it is the same in terms of its slope to the red line, you can see that it has a little bit of a different offset compared to the other one, which would contribute to some dark signal non-uniformity in that measurement. So this is critically important for applications that demand measurements performed across the sensor. So a really nice example of this is optical pyrometry. Optical pyrometry is a 2-color imaging technique that allows you to capture temperature information using a color high-speed CMOS sensor. In this case, it's looking at diesel injection and combustion. Optical spectroscopy is another one. This utilizes the entire sensor to investigate the wavelengths being emitted from a given test. So here we have a lithium and sodium emission upon combustion. And you can see that over time, we have these peaks of sodium and lithium increasing and decreasing. And the sensor non-uniformity or uniformity will have a big role in the accuracy of this measurement. Here are some concluding remarks and takeaways. When selecting a CMOS sensor for your imaging needs, always reference the EMVA 1288 specifications to determine how well a sensor will perform in your specific imaging application. When in doubt, request a demo system and do a side-by-side test. For low-light imaging applications, the most important specification is AST, absolute sensitivity threshold. It's important to remember that ISOsat has mistakenly been used for decades as a proxy for sensitivity. In fact, this is actually the opposite of what you generally want when you're determining what sensor to use, as the ISOsat simply tells you how fast your sensor will reach saturation, and it does not take into account any sort of noise value in the measurement. For applications that demand the ability to characterize nuanced details in your gray levels or your colors, the SNR curve is ideal to investigate. For applications that have a wide scene range, things like explosions, energetic impacts, welding, arcing, and others, dynamic range is going to be the key specification there. Bit depth of an ADC is commonly and incorrectly equated to sensor dynamic range. These are 2 very different specifications, and generally dynamic range is the applicable requirement that you want for your application. Some good reads and references and training. We have here a link to the EMVA 1288 manual. We put in here a good practices guide for digital image correlation. This has excellent information about how to set up your test for doing quantitative measurements on your frames. There's a link to technical articles from our Phantom applications engineers, scientific case studies, and examples. And if you're ever interested in taking one of our Phantom Academy of High-Speed Imaging courses, there's a link there for you to investigate what we have offered. Thank you everyone for listening. Do not hesitate to reach out to us with any questions you may have about this content, and please look forward to more webinars in the future. Have a great day.